Hey everyone, and welcome. Have you ever been curious about what really goes on inside a university math class? Well, today we're pulling back the curtain and unlocking the core ideas from a first-year algebra course. Now, it might look a little intense at first, but trust me, the concepts behind it all are absolutely fascinating, and we're going to break them down together. So let's jump right in. So just so you know where all this is coming from, everything we're looking at today is pulled directly from this source, a real deal first-year Algebra 2 tutorial from the University of Tipaza. We're not using a simplified version, we're looking at the actual material. So yeah, you open up the sheet and you see something like this, a bunch of letters, parentheses, and this weird little arrow in the middle. And if you're looking at that thinking, what on earth am I even looking at? You are definitely not alone. It honestly looks like a totally different language.
But that's exactly the point of what we're doing today. This isn't about sitting down and doing a bunch of complicated calculations. It's about understanding the language, right? It's about getting the ideas behind all these symbols. We're going to build that conceptual dictionary for you.
Here's the game plan. We'll start with a quick peek into what this course is all about. Then we'll define these universes where the math lives and the maps that connect them. After that, we'll see how to actually solve the puzzles, and then, the most important part, we'll talk about why any of this matters out in the real world. So let's get started. Part 1. Our first encounter with university algebra. What kinds of questions are even being asked here?
And the most important thing to get right away is that the goal isn't to just magically know the answer. The real first step is just decoding the questions themselves. When you see something like exercise 01 or exercise 03, you have to first figure out, what are they actually asking me to do?
Okay, so building on that, before you can play any game, you have to understand the playground, right? You need to know the rules of the world you're in. And in linear algebra, that world has a name.
At the very heart of all this is the vector space. Now, don't let the name intimidate you. The best way to think about it is as a universe. It's a collection of things we call vectors, and this universe has its own unbreakable laws of physics. Specifically, there are strict rules for how you add two vectors together and how you scale them. Stretch them or shrink them. And if a vector space is a whole universe, then a vector subspace is just a smaller, self-contained universe that lives inside the bigger one. The most important part is that this little universe has to follow the exact same laws of physics as its parent. It's its own little bubble, playing by the same rules.
And this is where the abstract idea gets real. This, E1, is straight from the tutorial. It describes a set of points in 3D space. But not all the points. It's an exclusive club for only the points that obey this one law. 2x plus 3y equals 0. And if you think about that geometrically, what you're really describing is a perfectly flat plane slicing through 3D space. That plane, that's our little self-contained universe. That's our subspace.
And this is a brilliant contrast. This is E2. Now, notice here there are two conditions, two laws that every point has to obey. X minus 3y equals 0, and z minus 5x equals 0. Having more rules makes us a much more restrictive, a much smaller universe than E1 was.
Okay, so we have these universes, these playgrounds, but things get really interesting when we start moving stuff between them. And that brings us to our next big idea.
This is the action part of our story. A linear map is basically a special function. Its job is to grab a vector from one universe and transform it into a vector in another universe, or maybe even the same one. But here's the key. It has to do this transformation while respecting the laws of physics of the space. It doesn't break the rules. Now, every map has two really important features, and these are exactly what exercise 03 asks about. First is the kernel. That's everything in your starting universe that gets completely squashed down to the 0 point in the destination. The second is the image. That's the set of all possible outcomes. It's every single spot you could possibly land on in the target universe, all the reachable destinations. So, now we have our dictionary. We know what vector spaces are, and we know what linear maps do. Let's see how those are the exact tools we need to start cracking the puzzles from that tutorial sheets.
So that first puzzle, prove that E1 and E2 are vector subspaces. Okay, so how do you actually prove that something is a valid universe? It sounds hard, but it's really just a simple three-step checklist. Number 1, does the universe contain a 0 point? Number 2, if you take any two things from inside it and add them, does the result stay inside? And number 3, if you take anything from inside and stretch it, does that also stay inside? If you can say yes to all three, then you've done it. It's a certified subspace.
Then, exercise 03 throws these words at us. Is the map injective, surjective, or bijective?
Okay, these are just fancy labels to describe how our map behaves. So let's just quickly break down what they mean. And this slide makes it super clear. Injective just means it's one-to-one. No two different starting points ever land on the same destination. Simple. Surjective means that every single possible point in the destination universe is reachable. The map covers the entire target. And if a map happens to be both injective and surjective, well, that's when we call it bijective.
All right, we have been pretty deep in this abstract world of rules and definitions. But it's time to zoom out and ask the biggest question of all. Why? Why should anyone who isn't a math major care about any of this?
Because this isn't just theory. This is the language that's literally running our modern world. Anytime you see a 3D model rotate in a video game, that's a linear map in action. How does an AI find patterns in massive amounts of data? By treating that data as vectors in a vector space. Machine learning, data science, even quantum mechanics, they are all built on this exact same foundation.
So here's the big takeaway. What looks like a boring, abstract set of rules is actually an incredibly powerful language. It's a toolkit for describing complex systems, for modeling change, and for manipulating everything from the pixels on your screen to the very probabilities of a subatomic particle.
And that kind of leaves us with one final fascinating thought. We've seen how just a few simple rules about adding and scaling things can build the engine for everything from video games to artificial intelligence. So the question to you is, what other parts of our world follow these same kinds of patterns? What other complex systems, maybe in economics or biology or even our social networks, are just waiting to be described and understood through the powerful language of algebra?